This is a chemistry application media project for colligative properties.
I'm Diego Camara.
I'm Braden Jarvis.
I'm Rocio Mendoza.
I'm Laura Silva. And our section is 560. The goal of the colligative properties lab was to find out the identity of the unknown compound. And we did this by using the temperature change values to find out the freezing point depression. And from that, we found out the molar mass of the compound. So what exactly are colligative properties? Colligative properties are properties that don't depend on the type of solute or the type of solvent that is being used, but actually depend on how much solute particles there are as well as how much solvent there is and the ratio between both. And these properties include the freezing point depression, the vapor pressure and lowering, the osmotic pressure, and the boiling point elevation. And what exactly is the freezing point depression? The freezing point depression is essentially a number that indicates how much the freezing point of a solvent lowered when a solute was added to the solution. And this is typically lower than the actual freezing point. And you can find it by finding the difference between the freezing point of the solution and the freezing point of the solvent.
We will use the principle of freezing point depression to determine the molar mass by isolating the molality. So we would first use the first equation to find the delta T. We will subtract solvent from the solute to find the change in temperature. Kf is already given. So now that we have delta T and Kf, we would rewrite the equation to find molality. Now that we have the molality, we can move down to the second equation. In the second equation, now that we have molality and the Kg as solvent, which is already used in the experiment, that's 15 milliliters of distilled water, we can rewrite that equation to find moles of solute. Now that we have the moles of solute from the second equation, and then we have the mass of solute from measuring it out in the experiment, we can rewrite the last equation to find the molar mass of solute.
The experimental setup was aimed to determine the freezing point of DI water at an unknown solution. The setup consisted of an ice water bath with a temperature probe which was used to record the temperature of the solution every 10 seconds once it reached 10 degrees Celsius. Then we recorded the points when the slope started to reach 0, and we proceeded to repeat the 3 separate trials with the unknown solution.
In results, we have a scatter plot of the temperature for the pure solvent and the representative example trial over the course of 100 seconds. And it is clear through the data trends that for the representative example trial, which contained a solution that had solute dissolved in it, it is a lower freezing point than the pure solvent. Next, we observe a table for the 3 trials, including the change in the freezing point in degrees Celsius, mass of the water in kilograms, mass of solute in grams, and the molar mass of solute in grams per mole. And the average molar mass was found by adding up the molar mass of the solute in the different trials and dividing by 3, which yields a value of 63.28924,073 grams per mole. The change in the freezing point was found by using the average freezing point temperature value for each trial and subtracting that from the average freezing point of the pure water. The mass of the water was found by subtracting the mass of the vial from the mass reading of the water and the vial, then divided by 1,000 to convert to kilograms. The mass of solute was found by subtracting the mass of the vial and water from the mass of the vial, water, and solute that was taken at the end of each trial. By using the equation delta T equals K times moles of solute divided by kilogram solvent, the moles of solute was solved for in each trial. This was then plugged into the equation for molar mass, which is molar mass equals mass of solute divided by moles of solute. Finally, for our conclusions for the identity of the solute, since the average molar mass is 63.28924,073 grams per mole, which is closest to that of urea, the solute is urea.